So in today's lecture, we're going to be going over branching and looping. Now, up until now, the code that we've written is very much what would be called straight line code, in that it always executes the same sequence of instructions regardless of what's happening. Now, obviously, we can do simple programs like that, and we could even do things that were slightly more complicated with use of conditional moves to try and get some simple conditional logic. However, if we want to construct any reasonably complex program, we're going to need to build higher level control structures. Specifically, what we're going to go through today is how we can build structures like simple if-else statements, as well as how we can build loops. Now, with having full control of how to do if-else statements as well as looping, we can kind of achieve the majority of general programming concepts that we may actually want to. So you can do simple or more complicated things in assembler pretty much after this lecture. We will obviously still do more complex structures like functions and things like that, but I feel like once you've grasped how loops and branching works, you have a much more solid footing to do more reasonable things in assembler. So the first type of jump statement we're going to go through is what's referred to as the unconditional jump, and by that it simply means that we will perform the jump regardless of what has happened before the jump statement. Okay, now a jump, or an unconditional jump rather, is equivalent to what's called a go-to statement in the language like C or C++. And in a high-level language, generally speaking, you're kind of instructed to avoid using go-to statements. It's seen as a bad coding practice. However, in the context of assembler, you pretty much have no choice but to use jumps. While most of the time you'll use what's called a conditional jump, you're still utilizing jump statements. So it's kind of a bit of a shift in the way we think, in that what is in some sense a taboo type of operation to use in a high-level language is kind of your only way of building these control instructions at an assembler level. But it does also mean that you can construct what's referred to as spaghetti code incredibly easily in assembler because you're relying on these type of jump statements. So the syntax for a jump statement is quite straightforward. So here we have a simple jump statement where we have JMP for jump, and we specify the location we wish to jump to. So basically the idea is in your code you may have some label and you will have a jump statement that will go to that label. Okay, so everything that is underneath that jump will get skipped, and when the program is running it will hit the statement and it will jump all the way to this line of execution and then continue from there onwards. So it's a pretty simple concept, but from which we can actually build more complicated programs. Now, the label is, in general, any label in the program's text segment. Now, it's something that's worth noting is that that's how you should be using these labels that you jump to. However, the assembler is not going to complain if you, for example, use a label from your data segment. If you do try and do that and jump to a location in your data segment, unless what's in your data segment is actually an instruction you've encoded, you'll actually almost certainly simply get a program crash because what you're trying to execute is not a real instruction. So the assembler won't moan, but you would get a runtime error if you did that. So a general rule of thumb is that your labels that you jump to should all be in the program's text segment. Okay, unless you're trying to do something very fancy, which won't be the case in this course. That could be a situation where you're trying to dynamically load instructions from a file to execute subsequently and things like that, but that's very specialized kind of programming. Now, in some ways you can think of a jump statement as giving you functionality similar to functions, in that I can, for example, have a bunch of different labels. So for example, F1, F2, F3, and I could, for example, jump to one of them depending on what I wanted to do. Now, while that's function-like in nature and that we can kind of have specialized chunks of code, it's not a fully fledged function by any means. It doesn't take parameters explicitly, at least. It doesn't have return types. So we'll get to more formal functions later on, but it's maybe a useful analogy at this point is that it has kind of this function-like behavior if you were to segment your code, such that given a different occurrence of something, you would jump to a different label. Now, how does the jump operation actually work? What is happening behind the scenes? So what actually happens is when you have a command like jump followed by a label, the instruction register, or RIP, actually gets updated such that the next instruction that it executes will be at the location of the label. Now, how it does that is actually a little bit more complicated because the manner in which you can set the next instruction register is dependent on how far away the next instruction is from your current location. So the simplest form is where we have an 8-bit immediate kind of jump. So basically this is a situation where I'm going to jump either 128 bytes back in the program sequence, so I'm going to jump backwards, or 127 bytes forward. Now remember in the last lecture where I discussed, say, the size of the different XOR statements, that's what I would mean in the context of the size of the instructions. So it's quite hard to actually figure out on the fly where these bounds would actually be. Now the next version of a jump is quite a lot more versatile. It's a larger jump, and it allows us to jump 32 bits or use a label that is 32 bits in size, and this basically gives us the ability to go back or forward 2 gigs in process space. So by and large, that's more than enough for everything that you would need. If you had a program that spanned more than that, more complicated things would have to happen, but for our purposes, that's not an issue. The shorter version of this jump actually takes up 2 bytes of space. Remember again, with for example, the XOR with 32 bits registers took up more space than the XOR, took up less bits than the XOR with 64-bit registers. The same thing applies here, that the short jump only takes up 2 bytes and the long version takes up 5 bytes. Now, at first glance, this might feel like a very complicated situation because you now need to try and keep track of how far you're jumping to the next function, and particularly, or next label rather, and particularly if your program is very long, that could be quite hard to deduce. Luckily, while assembler doesn't do a lot of things to help us, the assembler actually figures out which jump to use. So you don't actually need to figure out which type of jump it is. You don't need to figure out if it's going to actually be a short jump or a long jump. Now, if you actually check the instruction manual for the x86 64-bit architecture, to actually determine how to do the updates of ROP manually, it's quite a long sequence of if statements and special cases. So it's actually non-trivial. But luckily for us, we don't have to really worry too much about it. We just need to make sure we jump to a label in the text segment and our problems are kind of dealt with for us. But it is still informative to note that there's actually different kinds of jumps. So different distance jumps, a short jump and a long jump. And which one is invoked depends on how far away the label is from your current instruction. But once again, the assembler does that for us. So interesting to know, but it's not going to guide your everyday use of assembler necessarily. So what can we do with some of these jumps? So we're going to actually build to what's called a conditional jump, which is much easier to use. But in principle, we don't actually need a conditional jump. It makes our life easier to implement most programs. But you can actually emulate a conditional jump. So by that, I mean a jump that depends on some condition by actually using a conditional move as well as an unconditional jump. So using those two constructs, we can actually emulate a full conditional move. So let's demonstrate what I mean. So here's a little example of basically what would be an if-else statement. So the idea is I'm going to load the label A into a register. So I'm loading the label A into RAX. Note I'm not using the value at A. I'm actually interested in the label itself. So I load the label of A into RAX, load the label of B into RBX, and then I perform a conditional move. So in this case, I'm going to move RBX into RAX if the previous comparison resulted in a value that was less than 0. You see this by the -L. Now this is just an arbitrary example where I'm just saying, well, if the last calculation resulted in a negative value in essence, then I actually want you to load B's value into RAX, and then I want to jump to RAX, which means actually in the case that this conditional move happened, I will execute this part of the if-else statement. If this conditional move does not trigger, so the corresponding flags are not set, which means RAX remains A, then I will execute this part of the if-else statement. So we can get this if-else sequencing right, assumedly we do some kind of calculation, so for example a subtraction or something that would trigger the flags, and we can get this behavior. But it's a lot of extra logistics to get this conditional jump behavior, which we can kind of remove almost entirely by just using conditional jumps themselves. Now, something I should mention here is if we interpret this code as an if-else statement, you'll see that when I'm executing the if body, I will actually jump to another label at the end of it. So the reason for this is that, say I had something like if, ignore the conditional because we don't really have an explicit one, this was a bit arbitrary, but if I have an if-else statement and I was executing this on my language like C++ or something, say I invoked my if body, I would execute these commands that were in the if, and then I would execute commands after the else, which means actually what's happening is I'm jumping from this location over the else to the first instruction after the else body. And that's what's actually happening over here. Then once I get to this jump end, I'm going to jump over this else body and execute from this instruction onwards. So it's something that is happening in your high level code all the time, but you perhaps don't actually think about the sequence of instructions so much. So as I said, it's actually simpler to just use a conditional move, or conditional jump rather, which we're going to go through in a fair bit of detail now. But there's actually a nice interesting use case, which I want to go through from the book, because there's a couple of things inside this example that are maybe not incredibly clear just from looking at the book. So it's worthwhile going through how it all works. But the idea, at least, with the structure is we can actually build an efficient switch statement. Now, you may not often use switch statements, but it depends on what you're programming, but we can build a pretty efficient switch statement just using conditional moves and unconditional jumps, which kind of demonstrates the effectiveness of it. So the idea to make this work is you need an array of addresses and an index for that array to select which address you use to jump to. So the idea being is that you have some kind of array of addresses. So let's say we have address 1, address 2, address 3, address 4, and let's say this is index 0, 1, 2, 3. Now the idea is that you would change what index you want to point to. So maybe some computation happens, and based on what index you end up having stored in a register, you dictate whether you execute the function at address A, the function address at B, A2, or the function at location A3 or A4. Now again, sorry, this is not a function. These are just little bodies inside your switch statement. It's just easier to sometimes use the word function. But you would jump to the location that would correspond to that block in the switch statement. Okay, so let's actually try and implement this. You'll see it's actually in some ways easier when I show you the assembler. So this is a simple example. It's a bit artificial in the way it's set up, but it's to make the presentation a little bit easier to understand. So the first thing we do is we, in essence, actually have our little array where I have 3 data quads. One is for case 1, one is for case 2, one is for case 1, case 0, case 1, and case 2. And these labels correspond to labels in our text segment. Okay. Now, what is a little different in the way this data segment is presented to what you may have used before is you'll see that I only have one label that points to the first location. So the question is, how do I get to the second entity? And the way in which we do it is if I want the value at address switch, but I want, for example, this location here, or the value of that location rather, I simply use, say I was actually going for case 1, I would use switch plus 8. Now the question is, why plus 8? It's because I want to move one data quad down. So to get to the second element, I need to add 8. Okay, because each element in this case is a data quad, which is 8 bytes. If these were each data words, I would then use, for example, 2. Or if it was DD for a data double word, I would use 4. Now, you can actually extend this idea, and we'll go through this in a little bit more detail when we do arrays, but it's worth kind of mentioning it now, is say I wanted to get to a specific entity in this array, I could actually use a register times 8, and whatever value it was in the register would dictate which element. So if RAX was 0, I would actually just be looking at this first element because it would be switch plus 0. If RAX was 1, then we'd end up having exactly what I had over here, which would get me to the next element. And if RAX was in fact 2, we'd be going switches address plus 16, which would put me at this third element over here. Okay, so that's just some of the syntax. So with that in mind, let me just clear this up a little bit to make it easier to point to. Let's go through how this code works. So we have our 3 cases stored in our array at switch. You can think of as contiguous elements, but the way we access is kind of array-like. Then we're going to have a variable called I, which will dictate which case to set. So that's also going to be a data quad just to make things nice and straightforward. But this would be in an actual practical example where somebody was using the switch statement. That would maybe be read in by a user or something like that would determine what I is. But for the moment, let's just assume I has been set before we execute this code chunk. So we have our main function here, and we want to make sure we execute the case that corresponds to the value that is in I. So how do we do that? Well, the first thing I need to do is I need to extract I and store it in a register. So I need to put this into RAX. I could use a different register, but I need to get it out of memory into a register. And then I'm going to simply jump, and then instead of specifying the label, I'm going to jump to this specific element of the array. So in this case, it's going to move to whatever I was. So you see I is 2. So we're actually going to be executing case 2, which means once I jump, I will go all the way to this case 2. I'm going to move. This is just kind of a arbitrary design. The idea is if I is equal to 0, we're going to set RBX to 100. If it's 1, we're going to set it to 101. And if it is 2, we're going to set it to 102. So you'll see, because we're in case 2, we set RBX to be 102. And then we simply end our program. Now, if, for example, I was not equal to 2 and say it was equal to 1, what would happen is it would jump, instead of going to case 2, we'd be jumping to case 1 and execute the commands in sequence, or the instructions in sequence. And then when we get to this jump end, we'll jump to the end over there, and in this case we're setting RAX to 0 and returning. Okay, so it's a simple idea of how we can actually emulate a switch-like statement. Now we won't do this that many or that frequently, but it is something worth keeping in mind. One thing that's also a little bit odd here is you'll see I don't actually specify the size, and that's because the way in which jump works is that it assumes that all the labels are going to be 64 bits. The difference between the long and the short jump is not dependent on the size of the label. It's dependent on the difference in locations between my current address and the address I'm jumping to. So that's why it's generally smaller. But jump itself expects a 64-bit address. And in this case, all of our addresses were 64-bit, and you'll actually check if you inspect an arbitrary address like case 1 using GDB, you'll see it's actually stored as 64-bit. So by default, addresses are stored as 64 bits, and in 64-bit assembler at least. In 32-bit assembler, they're actually stored as 32 bits. But in 64-bit, all addresses are actually stored as 64-bit immediate values. So now that we've gotten a nice little working example using our conditional moves as well as our jump statements, you'll actually see here that we didn't need to even use the conditional move. But assumedly, at some point, we used a conditional move to depict what I should have actually been if we were using this in practice. Okay, so to the conditional jumps, this is where the most common kind of jump exists. So the way in which it works, or at least the general form of it, is we have a J followed by some kind of condition. So the CC just indicates that we're going to specify a condition followed by a label. The simple premise is that if the condition that we specify is met, we jump to that address. If not, we simply execute the next command. So if I have something like JZ, which I'll go through what JZ explicitly means, but just know it's a conditional jump at the moment, and I have location A that I want to jump to, and say I've got a bunch of extra instructions here, what will end up happening is if once I'm executing this line, if this condition is met, so my flags are set such that JZ is satisfied, I will jump directly to A and continue to execute. If, however, the condition is not satisfied, I'm just going to continue executing the next instruction. So directly what's beneath that jump statement. So that's how that will end up working. So what are the conditions we have available to us? Well, you'll see on the left-hand side, we have the general instruction names, as well as a set of aliases. So all this means is that they're equivalent conditional statements, but they use a slightly different mnemonic, because sometimes the interpretation of the other mnemonic is slightly more convenient for your logic construction of the program, but it means that they're equivalent. So JZ is equivalent to JE, and the same thing applies all the way down. So the first conditional jump we have is JZ, and that's basically a situation where I want to perform the jump if my last operation resulted in a value of 0. So say I subtracted two numbers and the result was 0. And the way in which it determines this is if the 0 flag was in fact set to 1. Now you don't generally manually set the 0 flag. You will perform some kind of computation, and the result of which will actually dictate that flag. We also have jump not 0, so if the last computation was not 0, JG, so this is jump if something is greater, and it simply means that if the last computation ended up resulting in a value that was strictly positive, we end up jumping. We then have greater or equal, so positive or 0. Jump less, so negative, less or equal, so less or equal, so negative or 0. We also have these two extra ones, which you probably won't use that frequently. There's a couple of places later on, but it's not the most common, is JC and JNC. And that's a situation where I'm going to jump if the carry flag was set. Okay, so it does a check on the carry flag, and then we have a JNC, so jump if the carry flag was not set. You can actually use that conditional quite effectively to deal with overflow, which is maybe the place you'll see it come up later, but it's not the most prevalent. The most prevalent are the sequence that you see at the top here. There actually are more than just these instructions, but these are the ones that are important to us and that we'll use in the course. Now, the way in which you can interpret the aliases are a little bit similar in that you see here for JZ, we have JE, which is for jump if equal. Now, that's because what is in general happening is you have some kind of operation before. You might have something like subtract, RAX, RBX. And if I perform the subtraction, then if they were equal, the result would have been 0. So equality and 0 are kind of seen as the same kind of flag. And the same thing applies for the later ones. You have jump not equal, jump not less or equal. You'll see why now it's sometimes useful to kind of have the negation, because I mean jump greater is pretty much the same as jump not less or equal, but you'll see why that's a useful mnemonic. And we have jump not less and so on. So those are the flags or the aliases we have available to us. Generally speaking, if we were in a normal kind of contact class session, in tests, I would actually always give you this table. So it's something that you should always have ready with you. But I wouldn't expect you to ever memorize a table like this. You'll generally have it given to you in a test situation if we're in a sit-down situation. Obviously online it's different, but if you're in a sit-down situation, I would always give this to you in an appendix. Okay. Now, the one issue with using those earlier operations is that they assume that some computation happened before, and now sometimes performing a computation before is not really necessary or what you want to actually do. So we could perform a subtraction and use the resulting flags that were set to determine what we do next, but you probably are not always so much interested in the result of that calculation. And that's why in assembly we get what's called a compare operation. And basically compare, so let's say I'm doing compare between two registers, RAX and RBX, is very similar to a subtraction between the two. The only difference between compare and subtract is that in the case of compare is it takes A and subtracts RBX, so pretty much like subtract, except it doesn't store the result anywhere, but it does set the corresponding flags of that result. So if they were the same and I subtracted them and I got a 0 value, the 0 flag would be set, and the same for the other flags. But compare doesn't store the result of that computation anywhere, whereas subtract stores the result in Rx, which means you're now storing a value that you don't necessarily need. Whereas with compare, we're able to do the computation, but we don't actually store the answer anywhere. So it's very useful for setting flags. And it's actually the default way that you'll set flags in a loop and things like that. There are some exceptions where you may not actually need to use the compare, but by and large, that's the predominant way in which you'll actually control the flags before you perform a conditional jump. So compare takes two operands, just like subtract, and the idea is it subtracts the second operand from the first and sets the appropriate flags, but no result is stored. The one thing is that at most one operand can be an immediate value, so it's just a limitation to keep in mind with compare. So let's look at an example. These first two examples I'll go through, you could have by and large actually done just using a conditional move, but they're simple enough so just that we can actually demonstrate the concept in a clear fashion. So what we wish to achieve with a bit of assembler we're going to go through is we want to construct the equivalent of this little if statement. So the idea is if A is less than B, I want to swap the two values. Okay, so straightforward enough, and for the sake of this example, assume that both A and B are data quads with some corresponding value in your data section. Okay, so with that in mind, let's try and recreate that C-like if statement in assembler. So the first thing I'm going to do is I'm going to pull A and B from memory. So I'm going to take A and store it in RAX, or the value at location A. Then I'm going to take the value at location B and put it in RBX. Then I'm going to perform a comparison. So in essence, what's actually happening here is I'm going A minus B. And I'm not storing the result anywhere, but I'm using the flags that it sets to perform my next operations. Then what's going to happen is I'm going to say, okay, well, if the result of this computation was greater or equal to 0, then I want to jump to in order. So let's kind of work through how this works. This expression over here is the same as me going A minus B is less than 0. Okay, logically the exact same thing. Now, what I'm actually doing with this jump is if this condition, so with this jump, if this condition over here is not satisfied, then I would normally have executed the instructions underneath. So if the condition over here, the general condition, is not satisfied, I'm going to jump over the body of the if and then continue to execute onwards. If, however, this condition is not satisfied, which actually means this condition over here is satisfied, I will execute the body of the loop. So it's kind of inverted to what you're used to in normal languages, because in a normal language like C++ or whatever, you would say, okay, well, if my conditional is satisfied, I execute the code body. Whereas the way you should think about it in the context of assembler is if my condition is not satisfied, I should jump over my actual code body. Okay. Now, logically, they're the same in terms of what we'll actually execute, but it's a little bit of a change of reasoning in the sense that I now need to actually figure out what is the situation when that conditional is not satisfied. And if it has not been satisfied, so in this case, if A is not less than B, then I'm going to jump over this if statement body and execute the next commands. And this is the reason we have those aliases, because you'll see here that greater or equal to is aliased with jump not less than. And what we actually had over here is we wanted to perform or execute the loop body if A was less than B. Or alternatively, in our assembler, I could say I want to jump over that if statement body if it is not less than. Okay, so if this conditional is not satisfied, I'm going to jump over and just execute what's afterwards. So JGE is the same as JNL. So jump greater or equal is equivalent to jump not less than. Now, you can obviously use whichever you find easier. I will by and large stick to this aliased form because I actually think it's easier to interpret when you have more complicated code. But in practice, you can use whichever is more comfortable for you. So let's look at a one step more complicated version. Again, you could do this with a conditional move, but we're kind of demonstrating the point. So I have another if statement where I say if A is less than B, I want to set max to be B. If that's not the case, I'm going to set max to equal A. So basically, I'm just setting max to be the larger of the two values. Now again, for this example, assume that A and B are data quad words. And now let's try and execute, or implement rather, this assembler. So first steps again, moving A and B into their registers. So I'm moving A into RX and B into RBX. Then I'm going to compare RAX with RBX. And now I want to jump to my else statement if that conditional is not satisfied. So jump not less than to the else block. And in that case, I'm going to move A into max. And we're done. If, however, this conditional is not satisfied, which actually meant that A was in fact less than B, I'm going to execute the if body, which means I'm going to set max to be equal B, and then I'm going to jump over my else statement to this end if, and then continue exiting. So you'll see again what's happening here is I'm jumping over the body of the else statement, like in that early example, because I can't execute both the if and the else part of an if-else statement. I only want to execute one of the two. So if I executed the if statement or if body, I need to jump over the else body. So now that we've kind of mastered the basic conditionals, we can actually start building loops. So we can construct many forms of loops just using conditional jumps. We're going to model our assembler loops after our typical C++ loops. So we're going to go through while loops, do while loops, and for loops. In this lecture, we're just going to cover the while loop variant. Though the other are quite similar, though there's some interesting performance characteristics of different loop structures. We're also eventually going to consider how to emulate breaks and continues statements in an assembler context. And obviously in a high-level language, concepts like break and continue can be avoided, though sometimes they can make one's code actually clearer. And the same thing holds true for a typical assembler loop. So let's go with kind of the first type of loop you may have encountered. We want to sum up the numbers 1 through 100. Okay, and there's a little typo in the heading. We want to sum the numbers 1 through 100, and we're going to do that using a while loop. So here's a little bit of C++ code to kind of give us a baseline before we implement the assembler. This is actually something worth considering, is that it may pay for you to write out what algorithm you intend to use to solve a problem, either in C++ or even in pseudocode, before you start writing the assembler. Now that's true in many situations, not just assembler, but you will find that your life will be a lot easier if you're not trying to solve both the logic problem and the assembler problem when coding assembler. You rather separate the two, so you kind of code it as you would in a higher level language, and then you actually implement in assembler. Separating the two will make your life much easier while you get into grips with assembler programming. When you're very fluent in assembler, you don't need to do things like that. However, when you're learning, I find it's actually quite an effective strategy to kind of bootstrap your time, because it means that you're focusing on the assembler aspect of a problem and not just the algebra or not just the algorithmic side. So merging the two can make things potentially unnecessarily hard. Obviously, this is a simple example, but what I say holds for more complicated ones. So here we have a sum equal to 0, and we're going to use I as basically our loop counter. We have a while statement, which is going to loop as long as I is less or equal to 100, and we're simply going to add the loop counter to sum, and then we're going to increment I and repeat. Okay, so very simple code, and obviously we're making the assumption that you don't know that in this case the number of, or the sum is actually simply going to be equal to this value. So let's say you've ignored the fact that you know from combinatorics what the sum of n digits actually is. Let's say you don't remember that, and we have to do this by the hardware. So we're going to implement this function now in assembler. So for the sake of this example, let's have our sum as a data quad in our data segment. So 64 bits, it can make things kind of as easy as possible. And now we have our code. So first thing I'm going to do is I'm going to set RCX to be 1. There's no reason I have to use RCX, though it's common convention to use RCX as your counting register. But again, you don't have to do that. It's just the common approach. So I recommend you do it because you kind of make it easier to interpret your code for other people reading your assembler. And now we have our loop body. Now you'll see here that I'm performing this indentation. So I have this while and end while. And these are two labels. The indentation is obviously ignored by the assembler. But I would advise, if you're in a situation later where we have nested loops, that you actually further indent the nested loops and kind of provide yourself as much syntactic-like structure as possible. The assembler will ignore it, but it can make your life easier. So in the same vein, it kind of helps to kind of have this indent. So here we have the while label and the end while label, both of which we will use. And you'll see, in some sense, you can think of this as kind of your open and closed brackets of your loop. They're obviously not brackets, but like you can visualize it as such. So the first thing we're going to do is I'm going to compare RCX with 100, because that's the comparison that we need for this. And if RCX is in fact greater than 100, so if this conditional is not satisfied, then I'm going to simply jump to the end of my loop. So I'm going to jump to while, because I've already iterated RCX enough and I'm done. I can jump to end while, and then it will just continue executing down there. However, if if the conditional has not been satisfied, if the conditional over here has been satisfied, it means that this jump will not happen. Then we actually execute the loop body. And in this case, it's quite straightforward. I'm simply going to take RCX, which is our I, and add it directly to what is in sum. So sum started over here as being 0, and I'll simply add 1, then 2, and so forth. Then once I've added the current index to sum, I'm going to increment RCX, and then I'm going to jump to the start of my loop. And then I will end up executing my comparison again, and the process repeats. But what is interesting here is that you really have two jumps. You have one conditional jump that is conditioned on the comparison that we perform. So that's how we set the flags. And then we have an unconditional jump at the bottom, which will always jump us back to the top of the loop. Okay? So it's something that is worth noting. Things are a little different if we have a do while. We have a slightly different structure, but we'll get to that in the next lecture. But the important thing to just notice, we have those two loops. So let's do something a little bit more interesting. I mean, that example was very straightforward. Let's try and count the number of ones in a quad word. So basically think of us having a bit string, a very long bit string of lots of ones and zeros. And I want to count how many ones are in that bit string. Now, there are a couple of kind of tricky ways to calculate this efficiently, but let's ignore that for the moment and let's do it in a direct fashion. We want to try and calculate the number of ones, and you'll see we'll actually use some of the bitwise operations. So we're going to start it in C++ again, and then we're going to rebuild it in assembler. So here we have our sum, which is going to store the number of ones that we're counting. We're going to use I for our index variable, and we're going to loop, in this case, while I is less than 64, because in a quad word, we have 64 bits, or 8 bytes. Okay, so first step is I'm going to perform this specific operation over here. So I'm going to AND the data. So in this case, data is the string. So this binary string here is my data. I'm going to AND that string with the value 1. So what in essence is happening here is, obviously 1 has a bunch of zeros, followed by a 1 at the bottom. And I'm going to perform the AND operation. Now recall from the last lecture that AND is a bit getter. So it will basically extract whatever the bit was in the original string. In this case, I'm basically saying I just want the lower order bit. Okay, I don't want anything else, I just want the lower order bit. So if the lower order bit of the string was 1, what will pop out here is 1 and a bunch of zeros. If the lower order bit was actually a 0, I would end up getting a 0 after the AND statement. Okay, so this gives me a nice way of either getting a 1 or a 0 depending on what the actual bit was. So we perform this AND, and then we simply sum the result, or add the sum rather, to our sum variable. So in essence, what's going to happen is if the lower order bit was 1, we add 1. If the lower order bit was 0, we add 0. And then what we do is we right shift our binary string, right ones. So basically I'm going to make the second order bit the new lower order bit. So I basically remove that original lower order bit, and now I repeat myself. So I'm going to increment I and perform the same operation again, which is going to basically extract the next lower order bit. So I work with the current lower order bit. So I work with the current lower order bit. So this bit here, I perform a shift, and now this is now my new lower order bit. Once I've extracted it again, I shift again, and now this becomes my new lower order bit. And I just repeat 64 times, which will cater for all of the bits in our string. So we're going to now rewrite this code in assembler. Now there are two ways, well there are many ways of doing it, but there is the way in which the textbook does this, which is not perfectly true to this C code. Okay, it kind of changes the way things are done. So I'm going to show you how the textbook did it, and it's perfectly workable solution. But then I'm also going to show you a slight tweak to the textbook solution that more closely matches the C code, just so you can see both ways, just so you don't think there's some weird magic that happened in the case of the textbook solution. So let's assume we have the following data segment to kind of make the code succinct. So we have our binary string, so in this case it's just this arbitrary immediate value we've selected. So it's very long, it's a full 64 bits, and our sum in our data segment just starts at 0. Okay, so now we have our code in our text segment. Now you'll start seeing this feature that I mentioned at the start of the course, where you see each line actually has a comment, which is not uncommon at all. You're not mandated to do it. We don't mark you on how well you comment your code, but it definitely will make your own life easier when debugging. So the first thing I'm going to do in this code is I'm going to move data into RAX. So basically I'm just taking the whole binary string and putting it into RAX, ready for us to process. And then I'm going to clear some registers to kind of prep them for future use. So the first thing is I'm going to, let's ignore this first one for the moment, but these second two are going to have very specific use cases. I'm basically setting RCX to be 0 with this command. Remember, if I XOR a 32-bit register, it 0 extends. So the XORing against itself sets it to 0, and it will 0 extend the other 32 bits. So this is going to be representing our I equal to 0. Then I'm going to use EDX, or more specifically RDX, as our sum variable, where I'm going to store all of the bits, and I'm going to simply XOR it out as well to make sure it's fully 0. Again, I'm using the 32-bit mode. For all of these operations, I could have very equivalently done something like this. I could have simply gone move RDX 0. It's the exact same operation. It takes up a bit more memory, but it does the same from a functional perspective. I often keep these XORs in these examples because the textbook alternates quite a lot. So I want you to be familiar with the different ways of doing it. But if you're writing your own code, there's nothing wrong with simply using the move because it's very clear. You don't need to worry about maybe misunderstanding something. By simply doing that, you'll definitely be storing 0 into RDX and you don't have to worry about it. But you still need to know how the other ways of doing it work. But when you write your own code, you can obviously pick. So we've set I and sum, or the registers at least that represent I and sum, to be 0. And EBX is a little different. We're going to be using EBX. We wanted to set it 0 because we actually want to use the lower 8 bits of it to extract a bit. You'll recall at the end of the last lecture, we demonstrated how you can do bit tests, and we're actually going to use bit tests for this assembly implementation to figure out what that lower order bit is. And we're going to use BL to actually get that lower order bit. So that's why we're clearing it out to start with. You'll see that will be a bit clearer as we go through the code. But setting I and sum to 0 is kind of immediately apparent. We now want to start our loop. So again, I have my while and my end while label. Again, you could pick anything. I mean, you don't have to call while an actual while. It's not a construct as such in assembly. You could call that A, and you could call this A, and you could call this B. It would make your code very hard to interpret, but nothing actually stops you doing it. So we have our while. I'm going to start with my comparison. It's going to compare RCX to 64. If RCX is in fact not less than 64, I'm going to then jump to the end of the while statement, and in which case I'm going to move RDX, because remember RDX was storing my sum, into my memory location sum, and then I'm going to set the return value to 0 and return. But obviously we're more interested in the case where we haven't already incremented RCX too far. So what's going to happen in this loop body? So the first thing we're going to do here is we're going to perform a bit test. So remember BT for bit test, and I'm going to check the 0th bit of RAX. So I'm checking the lower order bit of RAX. And then remember that this sets a flag. It sets the carry flag to be this value. So I want to gain the access to the carry flag. I want to extract it. So I'm going to use set C, which will basically extract the carry flag. And I'm going to store the result in BL. Now remember, to use the set C, I have to use these small registers, unfortunately. I have to use this 8-bit register. But because I already cleared it over here, I know it's fully 0. So I don't need to worry about there being things in the higher order bits that I don't want. So that's why I wanted to clear out the whole 64 bits. So even though I'm only going to be working with the bottom 8 bits, I know the rest is completely zeroed. Then I'm going to take what was actually in EBX and add it to EDX. Now, EBX is basically going to be all zeros right up until the lower order bit, which will contain the carry flag. So it's either going to be 0, 1, or it's going to simply be 0, 0. And then I'm going to add it to EDX. Now, I left this EDX because it's just how the textbook decided to do it, and it's because you know that the sum is at most 64 bits, but nothing would stop you having, instead of that instruction, having this instruction, add RDX, RBX. That would be perfectly fine as well, and if anything, I think it would be slightly clearer. But anyway, I'm just simply taking either a 0 or 1 and I'm adding it to my sum register. Then I'm going to perform a right shift of RAX. So basically I'm just performing this operation here, and this is so that I can do another bit test on the lower order bit. Once I've done that, I'm going to increment my count and jump back up to the start of my while loop. And then I just repeat this process again and again. Now, using this method of extracting the bits, you actually have some choices. The textbook performed the shift, but technically you could actually rather change which register you wanted to test and count it that way, and simply change what location you were counting the whole time. The only hook there is that you need to make sure that instead of using all of RCX, you can only use a small register, because that's how bit test works, but you could have implemented it that way. So with that in mind, I just want to demonstrate the way I could tweak this implementation here to be more close to this C implementation, so that it's very much more in line with this way of doing things. So say we didn't have access to a bit test operation, how could I implement the same thing? So the way in which we do it would be kind of straightforward, because what we were doing originally there is we were using bit test of the 0th location. We were retrieving the carry flag, which stored what the lower order bit was. So if the lower order bit was a 1, the carry flag would be 1. If the lower order bit was 0, the carry bit would be 0. And I was simply adding it to EDX. Okay, we could emulate more closely what the C code does as follows. I'm going to make a copy of RX into another 64-bit register. I'm just picking R8 because it's not in use. Then I'm going to AND R8 with 1, which is exactly what we did over here. And then R8 will contain a 1 if the lower order bit was a 1, and it will contain a 0 if the lower order bit was a 0, which means I can simply add R8 to RDX. Now in this case, I'm making it consistent with the way the textbook wrote this, in that it's assuming that we're working with a 32-bit register. That's why there's a D there. But for this exact example, you could have also just had RDX and have R8, and that would have worked perfectly fine as well, for this example at least. But I thought I'd mention this because it might feel like the textbook deviates a little bit from how the C code actually implemented something, but you could tweak it to be a closer match. But that's one of the advantages, I suppose, of working in assembly level, is that I have access to instructions like direct access to that one to test the original bits, and then I can extract it with the set C. But I'm able to test individual bits. It's not something you can natively do with a simple command in C++. Obviously, you could write a function to do it, but it's not something that's really built in. And that brings us to the end of this part of loops, and this is the kind of right up until before your semester test. You'll see in the next lecture so next week Friday, we're going to go through more advanced looping concepts and have nested loops and things like that.